All right, so you guys did some looking at rates, reaction rates, kind of by tracking a reactant or a product and all that. So how fast a chemical reaction occurs actually is going to be a math, go figure, it's math is involved. There's actually going to be 3 terms here multiplied by each other to ultimately come up with a reaction rate. And I like this because it kind of makes sense. So, you know, we've been talking about, like, if you have 2 reactants, reactant A and reactant B, you know, think of a reaction arrow going to form a product C. Well, if they're going to successfully, if A and B are going to be successful, then going to form a product, they need to collide. Okay, so that's actually a term we're going to come up with in part 2 something called the rate law expression, or the rate equation, rate law expression. And that's one of the terms. This makes sense too. Maybe, maybe not, but we'll be talking more about what happens behind the scenes. And I have a little animation to show you this. But basically, if A and B do find each other, if they do collide, as a function of like their collision frequency, they need to have enough energy to proceed. There's actually an energy barrier. Like if this is an energy diagram, you have to put a little bit of energy in to go back to go form products. Whether it's endothermic or overall exothermic, there's an energy barrier. Okay? And so you have to have enough energy. And then the other one, sometimes there's like a tail end or a this way or that way, okay? That's talking about orientation. They have to have the proper alignment in order to proceed to form products. So let's take a look at these little videos, which I hope work. But for instance, if we monkey with the concentration of the reactants, they're more likely to collide, okay? If we increase the temperature, they're more likely to have enough energy to overcome the energy barrier. Surface area of reactants, that could also be, are they able to collide? Presence of a catalyst. Catalysts, I don't know if we've talked about them yet. We'll be talking about them a little bit with regard to reaction kinetics. But a catalyst is an awesome thing. You remember catalytic converters, right? I don't remember much, but basically they provide a surface for a reaction to occur. They help with orientation. They help with that third term. Catalysts are not consumed. They just keep on ticking. Okay. So these are kind of some general statements about reaction rates. In the next soon, here in the next 5 minutes or so, maybe even sooner, I'm going to be talking about something that's part of the rate law expression or part of the reaction rate called the reaction order of a reactant. We'll be dealing mostly with positive reaction orders, but for things in general we're going to be dealing with, when you increase the reactant, it's going to increase the reaction rate. What does that mean? An increased reaction rate means it goes faster. Okay, so increasing the concentration of reactant should go faster if you have a positive reaction order. You increase the temperature, like I said, you give them more energy to overcome that energy barrier to proceed from reactants to products. Increasing the surface area, again, you have more likely successful collisions. And I mentioned a catalyst. So a catalyst is a player. Catalysts are optional. You don't have to have a catalyst. But if you do have a catalyst that's specific for the reactants to go to form products, it will always go faster. The presence of a catalyst will always make it go faster, and it won't be consumed. So these. Oh, we are cooking with Crisco now.
In the test tubes is hydrochloric acid.
Okay. So, on to something that you haven't turned in the homework for yet. All right. So how fast does a reaction occur? You guys looked at some data and turned me in some answers to that. So I mentioned the math, and actually we're going to build up to the three kind of prongs of how fast a reaction occurs. You know, will the reactants collide? Will there be a successful collision? Will they have enough energy, and will they be in the right orientation? Actually, all of that is going to have to be ultimately represented in what we call the rate law expression. Okay. So the rate law expression is a mathematical thingy okay? And it relates here on the, usually on the left, you'll see the word rate, and that actually is what you guys were working with, rate, how fast a reaction occurs, is equal to, then on the right, you're gonna see in brackets, molar concentration, okay, of the reactants, along with another couple variables. So rate law expression, you'll hear me or other people kind of talk about this expression in terms of rate expression, rate law equation, rate law, it's all the same thing, which is good or bad, I guess. It can be kind of confusing. Rate law expression, rate law, rate equation. So let's start with the simplest sort of generic, let's not name what your reactants are, but in fact, let's go ahead and make little a and little b, those are the stoichiometric coefficients of your two reactants, A and B, going to form products. Okay, so this is what I call, and I'll use it a lot, called the generic rate law expression. This is just generic. The rate, how fast it occurs, is equal to some constant K, and we're going to talk more about that K, times the molar concentration of each of the reactants, there's two, A and B here, raised to some reaction order, M and N in this case. So this actually is a convention we talked about in part one. These little subscripts means it times 0. So this would be the initial molar concentration of A. This would be at times 0, or the initial molar concentration of B. Okay, and this actually would be the initial rate, which is kind of a weird thing. You're like, because in order to get rate, you have to let it go on for a little bit, right? But think of it as basically kind of drawing a line tangent, if you want to. That at first, because what happens to reaction rates over time? They go slower. Okay, so the initial rate won't be the same as down the road rate. All right. So the initial rate is equal to K is the rate law constant. Now I want to say this not to confuse you, but honestly, we are going to, this is, can you see where this is a lowercase k, I hope. So in unit 3, actually, we're going to introduce another constant, and also is the variable k, but it's a capital K for equilibrium. Isn't that awful? You're like, dude, could you not, do something there? Okay, so the rate law constant K times the molar concentration of each of your reactants, and we usually use little m, little n. If there was a third one, like a third ingredient, a third reactant, we'd call that rate law, reaction order O, and then P, get it? Just kind of raise into it. So this is the, and actually those reaction orders, M and N, those are really, how do I say, raised to that power. On your calculators, there's x raised to the y, that's what you're going to do. All right. So, that first one, let's see, how do I say that? I had like drama here. Can you see the drama? Not really. But the red and the blue are trying to emphasize on this slide that this is very important. But the generic rate law expression, where rate is equal to your rate law constant K times the molar concentration of each of the reactants raised to the reaction order. The fact that there is a molar concentration, that actually addresses, like this says in black, the first of the 3 terms that we talked about at the end of part 1. That talks about the will they collide, the molarity. The increased molarity, they're more likely to collide, as long as your reaction orders are positive. Okay, so this is your important note here. Sometimes in this unit exam, I've gone with multiple choice questions for a section on your exam that you're going to have in a few weeks. And I will ask you, how do you get to those M's and N's? Those M's and N's are the reaction orders for A and B respectively, as I've just kind of described them. Reaction orders you can only get to by experimentation, only through experimentation. Now after you do the experimentation, there's a few ways to kind of massage the data and to get M and N, but you have to do experimentation. They will never be the stoichiometric coefficients. Now, I say that for a reason, because at the end of this unit, I'm going to tell you that it's a long story. But the stoichiometric coefficients are actually a player with molecularity if it's an elementary step. Okay. You got to do experiments. So sometimes somebody will ask you, and I'll tell you why it's important, but for the overall reaction, you need to know what the overall reaction order is, and guess what? You just add up the individual reaction orders, so it's not too bad. So in this case, where we have two reactants, and basically we're saying the reaction order of A is M, and the reaction order of the reactant B is N, as in Nancy, okay? How do you get the overall reaction order? You add them together. Overall reaction order. And that can be helpful. So, those reaction orders with regard to each individual reactant. We're going to, like I said, deal with mostly positive ones, I want to say, but they can be negative. They can be 0. They don't have to be whole numbers. They don't have to be integers. That's the second one. The third item up there is one we kind of looked at a minute ago, is that if your reaction order is positive, then any increase in that reactant, can you see mathematically, if you raise the concentration of anything to a positive power, your rate's gonna increase. That's what that means. Okay, if you increase this concentration and it's to a positive power, rate's gonna increase between those two. So when we get the ball going, especially later on, I really want to concentrate on not only positive reaction orders, but reaction orders of 0, reaction order, which is kind of an interesting idea. I'll show you what that looks like. Reaction order of 1 and a reaction order of 2, which is 0, first, and second order. All right. So when you guys handed in your homework for today, you came up with how fast a reaction occurs in moles per liter per second, or something concentration per time. All right? That's your rate. Well, look at it this way. I'm going to go ahead and I'm going to draw the generic again. Rate is equal to, this is the rate law expression. Rate is equal to some rate law constant K. And if we're reacting A and B, the molar concentrations of them raised to their reaction order. All right? We've talked a lot about dimensional analysis, factor label, blah, blah, blah. But if this has to be units of concentration per time, most notably moles per liter per second or per minute, okay? That's what these units have to be. Here's the deal. Basically, the way I look at it is this K needs to fix these units. I don't know if that makes sense, but that's what I'm going to show you here. And what units, I bet you're good with this. Remember, brackets means moles per liter. Okay. Big M there, molarity. All right. So if your overall reaction order, remember overall reaction orders, add M plus N. It can happen too. All right. If you add M plus N, okay, this is molarity. If you add the reaction orders and you come up with 0, it's kind of weird. Basically, anything raised to the 0 power, do you guys remember what that would be? 1. It is 1. Okay? So that will say actually that your rate has, how do I say this? Your rate has no dependency on molar concentration of anything there. Okay? So that's why actually your K in this case has nothing to fix. If it's 0, then your units of K are going to be actually moles per liter per, I'll go ahead and just do seconds. It could have been minutes too. Moles per liter per time. If you add them together and somehow your M plus your N is equal to 1, okay, then basically you have a moles per liter already running with this term over here. In order to get moles per liter per time, actually your K is going to be per time. That's it. Your units of K, I'll go ahead and change this to time. Your units of K are going to be per time. That's the units of your K. Now I mention this because sometimes we'll be working problems later on in this unit, and you're given K, and you're given the units of K. And if you're given the units of K, by golly, you know something about the reaction, of the overall reaction order. If you only have one reactant, guess what? You know its reaction order off the bat. Then the last one is if your overall reaction order is 2, okay, basically you have moles per liter squared. You have moles per liter, let's see, how do I say that? Moles per liter squared. And somehow you need to end up with moles per liter per time. So that's why, I know it seems kind of strange, but basically you're going to have liters per mole per time are going to be units of your K. It's just got to be that way. Put another way, it's basically the inverse of molarity and time also down here. Okay, so these units of K, that's why I say it feels like to me it has to fix whatever's here to make sure your rate is in concentration per time. All right, so put another way. If it's overall 0 order, then like I said, it needs to be, I put moles per liter per time. You could think of it in any of these, right? They all say the same thing. Overall reaction order of 1. Okay, inverse time basically. A couple ways to do that. Overall reaction order of 2. You have the inverse of moles per liter and inverse of time basically. 4 liters per mole per time. Or moles per liter to the -1 power times the -1 power. Okay, so the rate law constant, little k. All right, well let's look at some data. It kind of seems kind of strange data, but let's just, again, we have A reacting with B, going to form products. Okay, and this is, remember, your kind of, this is your generic rate law expression down here. And just for kicks, we're going to say that our initial molar concentration of A, we're going to go with it at first at 0.20 moles per liter. Okay. And then we're going to run a second experiment, and this is how this is done. Remember, we can get to rate law, we can get to reaction orders only through experimentation. So let's say we run it a second time, and we're going to double the concentration, or 2 times the initial concentration. So now instead of 0.2, we got 0.40. Let's see what we would expect now, going with different reaction orders for A. Mathematically, what would that look like? So in this case, and we do this a lot, and we take advantage of this, we are going to hold B constant for all of these, for both of these trials, okay? And the K is going to be constant. The K will not change. The rate law constant K is specific at a specific temperature, but we're not going to monkey with the temperature, so K stays the same. All right. So doubling it from 0.2 to 0.4. Now, you see at the top there where I've rewritten my generic rate law expression? Notice I've simplified it. And the reason is, think of it this way. Okay, in this actually, this is constant. Rate law constant, right? And actually, this is also constant this time. Just because I did. So actually, sometimes we say, anytime you see that prime, that's actually pseudo, pseudo, pseudo constant. Okay, if something's a pseudo constant, it's kind of like a constant. So that pseudo constant there actually is equal to the real rate law constant K times the molar concentration of B raised to its reaction order N. That's that. All right. Now, back to doubling the concentration of A. So I went with 0.2 and 0.4. Here they are. The 0.2 and the 0.4. Those are the molar concentrations of A. Now, if we go with the reaction order of 0, we are going to raise the molar concentration of A to the 0 power, molar concentration of A to the 0 power. And like Andrew said, that's equal to 1. In both of these cases, I can increase the concentration till the cows come home, and it has no effect on the rate. With this sort of data given to you, this is called by inspection. If you want to put by inspection up here, you can, because you might be referring to this later. Actually, I printed this one out for me. So just by inspection, you can wada boom say the reaction order of A is 0. Done. End of it. Well, let's look at something a little bit different. Remember I told you that reaction orders don't have to be integers. So here we're going in with a reaction order of plus 0.5. Reaction order of 0.5. Relatively speaking, the changes in the rates, we should see it going from, relatively speaking, 0.45 to 0.63. We increase the concentration of A from 0.2 to 0.4, and it's going to go from 0.45 to 0.63. So if you divide, and actually this is one of the things you're going to do with your homework, if you divide 0.63 by 0.45, you will get the value of 1.4. Hold that thought. So it increases by a factor of 1.4. All right, let's go to the more common ones. So we did 0, 1, and 2 were the 3 most common ones. So from 0.5, let's go to 1. All right, so you take the 0.20 and the 0.40, you raise them to the first power, and of course you have 0.2 and 0.4. That's the relative rates. If you take the higher rate divided by the lower rate, you get actually 2, right? A factor of 2. 0.40 divided by 0.20 is 2. So your rate is doubling. It will double. If anything, if your reaction order is 1, and if you double the concentration, your rate will double. It's by inspection. Last one. Okay, let's say your reaction order with regard to the reactant A is 2. So that means we need to take the molar concentration, raise to the second power, and over here with the higher concentration, the molar concentration raised to the second power. Do this on your calculator and you get 0.040 for the relative rate at the lower concentration, and you'll get 0.16 at the higher concentration. Again, if we go ahead and take a ratio of this higher rate divided by the lower rate, you are going to come up with a factor of 4. That number will be 4. Your rate quadruples. So this is a factor of 2. This is a factor of 4. Corresponding to a reaction, corresponding to a reaction order of 1 and 2 respectively. Over here, no change in the rate, reaction order of 0. You can use this by inspection. Or you can deduce. If somebody runs a pair of experiments for you, it has to be doubling though, doubling the concentration, look what happens to the rate. All right. So what you'll want to do, we're going to do an example here. And to apply this, basically, you need to find a pair of runs, kind of like the 0.2 and 0.4, a pair of runs where the concentration's been doubled. It's a little bit of a catch because in the example we're going to look at, there's more than one reactant. So in your pair of runs, the only thing that can be changing is the reactant of interest. You have to find it one reaction order at a time. Okay. So all parameters except for the concentration of the reactant of interest needs to be held constant. Okay, the initial rates will be measured. So then, if you see a change in the rate of the reaction, then you have narrowed it down to only because of the influence of changing the concentration of one reactant. I guess I should mention these guidelines are much broader than if you simply have a pair of runs where you doubled the concentration. Actually, we're going to have to change it up a little bit. Life's going to get a little more complicated for our second example, and the concentration wasn't exactly doubled, so we can't use by inspection. But still, this will hold true, this approach. So the only way you can get, and I'll go over here and say what they are, I call them the superscripts. The only way you can get the reaction orders, M and N, as I've described them up here, is by experimentation. Experimentation. You think in this day and age we could get to it some other way, but you can't. So once you've got your data, these are the three things that you can do with your data. You can get to the reaction orders by inspection. We're going to do that first. And actually, I think we'll have time today. You can also get to the reaction order algebraically, if it wasn't doubled systematically like that. And then on Wednesday, we'll talk about how do you do a run and get to it experimentally, or excuse me, graphically, using a graph. Okay, so this is what we're going to do. So just to kind of, so we're all on the same page, if I were to work this as an experiment, you can already see on the next page, I'll give this to you. You can already see on the next page, this is what it looks like. But to kind of get my wits about me, I probably would write that generic equation just because I like to. I think it buys me time. It's kind of like, I make doodles. So rate only focuses on the reactants. So rate is equal to some rate law constant K, and actually we'll get to that here in a minute. We'll find a real value of that, times the molar concentration of each of the reactants raised to the reaction order. So I'll just start with H2O2 raised to the M times the molar concentration of I minus raised to the N times the molar concentration of H plus raised to the O. That's probably how I would start this. So, we are supposed to do this stuff. Okay, I kind of gave you my generic equation. It says you are supposed to come up with the reaction order. So on what I just gave you, can you see where that's the superscripts M, N, and O? The reaction order for each reactant. Next, and actually I'm going to wait to kind of show you what this is, or in your margins if you want to, we are going to, once we have these reaction orders, then we can come up with K by substituting, I'll just put the word substituting in for one experiment of your choice to find K. We'll see how that works. And to me, and sometimes I'm not as clear about this during the semester as I'd like to, when it says give the appropriate rate law expression, that means actually you're going to rewrite that generic thing. So you're going to rewrite this rate is equal to, and then you'll have a real value for K, real K, okay, times the molar concentration of each of those raised to their, you'll have the real M, N, and O. So I'll just put this way. You're going to have real values, real reaction RxN orders here. Okay. All right. So let's do this thing. So it would run 4 times, and when you're set with, when somebody gives you data like this, you should start thinking, now why did they pick those runs? Okay, so actually here in a minute, let's see, how do I want to say this? Can you see, for instance, if we pick on experiment 1, experiment 2, can you see where the I minus and the H plus are constant? So that would be a good one to get to the reaction order of H2O2. And then switching it up, can you see where, looks like if we look at 1 and 3, okay, 1 and 3, the H2O2 is constant and the H plus is constant, and 1 and 3, what we're doubling is the I minus. So 1 and 3, if we compare the rates, 1 and 3, and look for the effect, whether it's held constant, 0 change, doubled, or quadrupled, that's what we're looking at, 0, 2, or 4, we can get to the reaction order for I minus. And last but not least, yep, you see 1 and 4, right?
So if H was doubled and I was doubled?
That wouldn't be a good pair to pick.
Right, but would it be 4.60 times negative 6? Is that what it is?
If the H plus was doubled and what was doubled?
I. Well, I don't need
The I minus. Well, I think what we're going to see is there is no effect. The H plus is actually 0 order, so but I think you're on the right track. I do.
So I guess that was a bad example. So if it was I, then the H2O2, then that really would be.
Oh, I see what you're saying. If they were both first order, would it be? But you don't know if you're confounding your experiment, because maybe one's second order, if it would quadruple, did you say? Yeah. If they were both first order, it would quadruple, and if one was second order and one was 0 order, it would also quadruple. So, but you're thinking right. But ideally, this is just by inspection. Okay. So your hints then are to pick a pair of experiments where only one of the 3 things is changing. And I'm thinking I would go with experiment 1 and 2, experiment 1 and 3, and then I think I said experiment 1 and 4. But it wouldn't always be that way. All right. So you've got it, you can go back and forth. You can go on to the sheet I gave you if you want. But experiment 1 and experiment 2, the thing is, and I didn't mention it, but are you guys okay with this? Basically, what you need to do is go over to this last column, okay, and divide the higher concentration, the 0.020 molar concentration of your hydrogen peroxide. Divide that rate, 2.30 times 10 to the negative 6, by 1.15 times 10 to the negative 6, and you get a factor of 2. If you divide this by this, you get a factor of 2.
Okay.
Yep. And since it's doubled, that's why I kind of printed this out for myself. See, since it's doubled, and I said by inspection, you were supposed to put by inspection, you go over here and you see the double, and you see that it must be the reaction order of 1. And if we compare 1 and 3, also, 1 and 3, the only thing that's changing is the I minus, and it's being doubled. And again, if you divide that 2.30 times 10 to the negative 6th by the 1.15 times 10 to the negative 6th, you'll get 2, which is doubled. So it also is reaction order of 1. But if you would have divided those two and got a 4, that's a quadruple, and that goes with reaction order of 2. Yeah, if you would have gone over here and say instead of, let's see, well, 1.15 times 4 is 4.60, yeah. So if this is 4.60 times 10 to the negative 6th, you would divide this rate by this rate and you get a factor of 4. This rate by this rate, you get a factor of 4. And it's 4 because you doubled the I minus between 1 and 3. Then that would have been, quadrupling would have been a reaction order then for I minus of 2 instead of 1. And then last but not least, yeah, I kind of let the cat out of the bag for hydrogen. So for hydrogen, we're going to go with 1 and 4 just because it's convenient and because they've already kept the H2O2 and I minus the same for 1 and 4. Okay, but they doubled the I minus. But when it comes time to go ahead and take a ratio of the rates, notice it's 1, right? This one divided by this one, they're the same. So the reaction order of the H plus is 0. Okay, so we can actually take our generic rate law expression that I kind of took out of the bag a minute ago, and now we can start putting in numbers for M, N, and O. For the reaction order of H2O2, variable M, we said it was 1. For the reaction order of I minus, we said was N, was also 1. And then the reaction order of H plus is 0. So of course in your final rate law expression, that last term's going to go away because anything raised to the 0th power is 1. Okay. So this would be one form of your final rate law expression where we don't have the variables M and N anymore. And notice that anything raised to the first power can be shown just by that thing. It's implied that those are raised to the first power. These are reaction orders of 1. Okay. Now we need to find the value of K, and we get to pick any of those 4 experiments, basically. You pick a line, and you take that last number, it goes here. You pick an experiment, you take the molar concentrations of those, they'll go in, those molar concentrations on here. Like if you pick the first one, I think that's what we're going to do. This number goes right there, great. Okay. The molar concentration of H2O2 goes there, raise to the first power, molar concentration of I minus goes there. Okay. And then all we have is K to solve for. Okay, so find the value of K. Once you have your reaction orders, which we do, we can pick any one experiment and substitute in. So a little bit ago when I said substitute, this is what I meant. Okay. So we can go ahead and take the rate law expression if you want to kind of rearrange it. And so K, which we're after, is the initial rate divided by the molar concentration of the H2O2, also in the denominator, the molar concentration of the I minus. We came up with reaction orders of 1, so those are both raised to the first power. So from experiment 1 then, K is equal to that 1.15 times 10 to the negative 6th. And that's a rate, so that's moles per liter per second, divided by 0.010 moles per liter, the hydrogen peroxide concentration. Also in the denominator, the I minus concentration, 0.010 moles per liter. And so unit-wise, let's make sure that this is going to work, or we'll see what units of K will be. Actually, do you guys buy this? This is the overall reaction order. What is the overall reaction order here? It's 1 + 1 or 2. So honestly, we should be looking at units of this over here. So let's see, moles per liter cancel, and we're left with still 1 moles per liter in the denominator, and we have units of time in the numerator. Ugh, oy vey. So basically, in the numerator we have 1/seconds, and the denominator we have moles per liter, which actually we can bring it up if we take it, take the inverse of it. So those are what your units are going to be. And number-wise, okay, the number is 0.012, and our units are wonderful. We got units of liters per mole per second, which is what we should get if it's overall second order. And overall order, remember, is you sum up or add up the individual reaction orders, which was 1 + 1. Reaction order H2O2 we said is 1. Reaction order of I minus is also 1. Okay, so we aren't going to get to the others, the algebraic approach, but let's take a look at this one. This one's by inspection. So this one will be due on Wednesday, and it looks like this. Okay. So four experiments, right? A plus B going to form something, C and D, I guess it says. The initial rates are given for these 4 trials. And again, it's by inspection, which means you should be looking for doubling in concentration. So I went ahead and wrote the generic rate law expression. You know, rate is equal to K times A raised to the M times B raised to the N. Okay, so in green there I say find a pair that something that, in this case, if you look at experiments 1 and 2, A is held constant, but B is doubled. And if you're like me, you have to concentrate. Is it really doubled? Say 0.133 to 0.266. Yes, it is doubled. Okay. Well, if that's the case, then I should be able to take a ratio of the rates. So actually, I'm going to take 1.35 times 10 to the negative 3rd divided by 3.35 times 10 to the negative 4th, and I'm going to look to see, is it a doubling? Is it a quadrupling? Definitely doesn't stay the same, right? So I'll hold up this again. You should be able to find one of these 3 scenarios. 0, no change. If it's first order, it's going to be doubled. If it's second order, it's going to be quadrupled. Did you get a number, an integer-ish? Okay. You didn't? Okay. Well, you should. So you'll do that for B then, to get and for B actually it's going to be a little bit different. My hint there is you look at experiment 1 and 3 to get B. The reason is that, notice that, you look for 1 and 3 to get A. I said that wrong. Look at 1 and 2, that'll get you the reaction order for B. Look at 1 and 3, that'll get you the reaction order for A. The overall reaction order is, that's my favorite one to do. You just add them together and come up with the value of K. That's where we said you get to pick one of the 4 trials. You didn't come up with an integer?
I didn't do it.
Okay, you should. So pick one and substitute in for the rate for that experiment, the molar concentration of A, the molar concentration of B, and by then you should know what power to raise them to, because you figured out M and N. All right, so this will be due Wednesday. I'll go ahead and post this. It's all good stuff. Any questions?